In the last video, you learned that it's possible for an object to have either a positive charge, a negative charge, or be neutral. A neutral object has about the same number of positively charged protons and negatively charged electrons. If an object acquires a negative charge, that means it has more negatively charged electrons than positively charged protons. If it has a positive charge, it has more positively charged protons than negatively charged electrons. These two balloons here are approximately neutral, and my head is approximately neutral. But now I'm going to change that situation by rubbing these two balloons onto my head. Rub them on there nice and good. Let them go. And as you can see, the two balloons are now repelling one another. In the last video, it was pointed out that if two electrically charged objects repel, it's because both objects have the same type of electric charge. Either they're both positive or they're both negative. If two objects attract each other electrically, that means that one of them must be positively charged and the other must be negatively charged. And as you can see here, these two balloons are repelling one another, so they must both have the same type of electric charge. For the sake of argument, let's say that electric charge happens to be negative on both balloons. If that were true, would that mean that negatively charged electrons were rubbed from my head onto the balloon? Or would that mean that negatively charged electrons were moved from the balloon onto my head? That's right. The electrons must have gone from my head onto the balloon because electrons themselves have a negative charge. So if I put more electrons on each balloon, that's going to give them an overall negative charge because there will be more electrons than protons on the balloon if that were the case. I'd also like to point out that protons in general don't move from one object to another. They're sort of locked inside the nuclei of the atoms that make up the object. So anytime an object acquires an electric charge, it's because electrons have been moved onto the object or removed from the object, not protons. Well, if the balloons have a negative charge because they have excess electrons, what kind of charge would have to be on my head if electrons move from my head onto the balloon? Well, that's right. My head would have to have a positive charge. And if my head has a positive charge, would it attract or repel the negatively charged balloons? That's right. It should attract. So let's make a prediction here. When I bring my head close to the balloon, my head should attract the balloon. Let's see if that's what happens. I bring my head close, and sure enough, the balloon is attracted to my head. The little internet film you just saw talks about Coulomb's law, and I'd like to say a few more words about Coulomb's law and do some examples for you. So in the film, you found out that if you have two objects, both of them have some kind of electric charge on them. So we'll call the electric charge on object 1 Q1, and we'll call the electric charge on object 2 Q2, that there's going to be some kind of force between them, either attractive or repulsive. Let's suppose you want to know what the force is on Q1. And so we're going to call that F12. That notation means the force on object 1 due to object 2. They said that was equal to 1 over 4 pi epsilon 0 times the value of the charge on object 1, which we're going to call Q1, that would be in coulombs, times the value of the charge on object 2, which we'll call Q2, that's also in coulombs, divided by the distance between them squared. Actually, that's the distance between their centers squared, so that would be r. And then we multiply that by something called the unit vector r hat. Okay? What is this unit vector? Basically, it's a vector that's 1 unit long that goes from the second charge toward the first charge. So this would be unit vector r hat and its length would just be 1 unit. Okay? So if if both of these charges were positive, there would be a repulsive force, and therefore the force on Q1 would be kind of off to the left, which would be in the same direction as the unit vector. Okay? So that would mean, let's say Q1 and Q2 were both positive. That means this whole thing here would be positive, and the direction of the force on 1 due to charge 2 would be in the same direction as the unit vector if there was a repulsive force acting on Q1, which would be true if both charges had the same type of charge. If one of these charges were negative, then one of these numbers would be negative, and that means this whole coefficient here would also be negative. And that means that the direction of the force on Q1 would be in the opposite direction as the direction of the unit vector. Okay? So imagine that, let's say, this charge is positive and this charge is negative, and therefore there's going to be an attraction between the two charges. That means the force on Q1 will actually be to the right in this case, and that's in the opposite direction of the unit vector. Hence the negative sign that we get here for the coefficient. Means that the final force would be in a direction opposite that of the unit vector. Now, in my opinion, this whole way of doing things is a little bit scarier than it needs to be. So let's just forget about unit vectors, and let's forget about epsilon 0 here. And then let's write the equation for Coulomb's law in the following way. F is equal to K Q1 Q2 over r squared. We're going to forget about the unit vector here. And we're going to let k equal 1 over 4 pi epsilon 0. And when you work all that out, that means that k is equal to 8.99 times 10 to the 9th, has kind of crazy units here, Newton meter squared per Coulomb squared. And I think that makes the equation a lot nicer looking. Within the context of a problem, you'll be able to figure out what the direction of that force is. This will just give you the magnitude of the force in newtons. Okay, so let's do a simple example with Coulomb's law. Let's suppose we have two mylar balloons, and we'll call this balloon number 1. And we'll call this balloon number 2, make it a little bit bigger. And let's say the distance between the centers of these balloons is equal to 0.50 meters. And the electric charge given to balloon number 1 is going to be positive 2.0 times 10 to the minus 7th coulombs. And the charge on balloon number 2 is going to be negative, so minus 3.0 times 10 to the minus 6 coulombs. So that means that the magnitude of the force between these two balloons, we'll call that F, is equal to K Q1 Q2 over r squared, which is equal to 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. That's Coulomb's constant K, times the value of the first charge, which is plus 2.0 times 10 to the minus 7th coulombs, times the value of the second charge, which is minus 3.0 times 10 to the minus 6 coulombs, and all divided by the distance between their centers squared, 0.50 meters squared. Now, if you do this on your calculator, I'll do that over here. Some people misuse their calculator, particularly the features for inputting numbers in scientific notation, so I want you to follow along with me here. I'm going to input this as 8.99, And then some people use the 10 to the x key. You shouldn't do that. You should go second function and then the comma here, which is second function double E. That stands for exponent. And then you type in the exponent here, which is just 9. And notice what it says here. It says 8.99E9. That's the same thing as 8.99 times 10 to the 9th. I want to multiply that by the first charge here, which is going to be 2. Don't have to put the 0.0, obviously. Again, second function, double E, minus, using the minus key down here for sign, minus 7. That's the same thing as 9 times, that's the same as 2 times 10 to the minus 7th, okay, times negative 3, second function, double E, minus 6, divided by 0.5, and then I'll hit the squared key here. Notice I never hit enter until now. That's minus 0.022 newtons. How do I get newtons out of that? Well, if you come up here, the coulombs squared here are going to cancel out these 2 coulombs. And when I square the meters here, it's going to cancel out that square meters. And then I'm left with newtons. The significance of the minus sign is that this indicates that there's an attractive force between the 2 balloons. If my final answer were positive, it would indicate a repulsive force. So this is my answer. 0.022 newtons, attractive. Do a little more complicated problem involving Coulomb's law. Let's do 3 charges that lie along a straight line here. So maybe this balloon here we'll call charge number 1. And this balloon here we'll call charge number 2. And this balloon out here is going to be charge number 3. And all of these charges lie along a nice straight line. Let's say the distance between the centers of charge number 1 and charge number 2 is 0.40 meters. And the distance between charge number 2 and charge number 3 is 0.60 meters. Let's make the charge on balloon number 1, call it Q1. It's positive, 1.0 times 10 to the minus 7 coulombs. We'll make the charge on balloon number 2, we'll make that plus 8.0 times 10 to the minus 7 coulombs. And we'll make a charge on balloon number 3, we'll make that negative 2.0 times 10 to the minus 6 coulombs. Okay? Now, in the first example, if the force turned out to be negative, that would have been an attractive force. And if the force turned out to be positive, that would be a repulsive force. But when we're doing more complicated problems, it's probably best to abandon that convention and just take the magnitude of the force and then figure out which way it's acting and then put in the minus sign or the plus sign for the direction of the force as necessary. So, in this case, what I want to find out is what is the force on balloon number 1 due to these other 2 balloons. So there's going to be a repulsive force between balloon number 1 and balloon number 2 because they both have the same charge, type of charge. And that's going to drive balloon number 1 off to the left, which we're going to make the negative direction, off to the left. Okay? There's going to be an attractive force between balloon number 1 and balloon number 3 because they have opposite charges. And that attractive force is going to want to drive balloon number 1 off to the right, which is going to be the positive direction. So when we're figuring this out, we want to make sure we're doing this properly with our directions here. So the way I'm going to figure this out is figure out the force on balloon number 1 due to balloon number 2. And I'm going to add that to the force on balloon number 1 due to balloon number 3. So that's what this notation means, okay? So let's look at the force on balloon number 1 due to balloon number 2. I'm going to write it in the following way. I'm going to write as negative absolute value K Q1 Q2 over R12 squared. This is the distance between balloon number 1 and balloon number 2. I could write that up here. And I'm going to take the absolute value of this to force it to be positive. But then I'm going to make it negative by putting a negative sign out there, because I already know that the force between these two balloons is going to drive balloon number 1 in the negative direction. And I want to make sure that's reflected by my calculation. So that's going to be negative 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times 1.0 times 10 to the minus 7 coulombs, that's the charge on number 1, times the charge on number 2, which is 8.0 times 10 to the minus 7 coulombs, all divided by the distance between these two squared, which is 0.40 meters squared. And I'll finish the absolute value bar over here. Okay, so that's what we're trying to figure out. If we work this out on our calculator, what we get is 8.99 double E 9 times 1.0 double E minus 7 times 8.0 double E minus 7 divided by 0.4 squared. That's all going to be positive, but I'm going to force it to be negative here, because that's the direction I need. So what I get is 0.045 newtons in the negative direction. Okay, so again, this represents the force between balloon number 1 and balloon number 2. The significance of the minus sign is that this will be a repulsive force, but that has the effect of pushing balloon number 1 in the negative direction, off to the left. So that's why we need a minus sign there. So now let's figure out the force between balloon number 1 and balloon number 3. We'll call that F13. Now it's going to be an attractive force, because this is a positive charge and this is a negative charge. And the attractive force is going to have the effect of pulling balloon number 1 to the right, which is in the positive direction. So I want to make this a positive sign. Again, an absolute value, KQ1, Q3 now, over R13 squared. Now R13 is going to be the total distance between balloon number 1 and balloon number 3, which is actually equal to 1 meter. So R13 is equal to 1 meter. So coming back down here, this is going to be 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, as usual. This is going to be the charge on Q1, which is 1.0 times 10 to the minus 7th coulombs, times the charge on balloon number 3, which is minus 2.0 times 10 to the minus 6th coulombs. Close that absolute value sign here. Divided by the distance between these two balloons squared, which is just 1.0 meters squared. So, doing this on my calculator here, this is 8.99, second function, bring this up here, double E, 9 times 1, second function double E minus 7, times minus 2 second function, double E minus 6, divided by, well, 1 squared is just 1. We'll just 1 squared anyway. And hit enter. And we get, well, it's going to be a negative number, but remember, overall, we want it to be positive. So this is going to be positive 0.0018 newtons. Okay. So that represents the force between the first charge and the last charge. Now all we have to do is add these two together to come up with a final answer. So the force on balloon number 1 is equal to this plus this, or negative 0.0045 newtons plus 0.0018 newtons. And do this in our calculator here. Negative 0.0045 plus 0.0018, and that's equal to negative 0.0027 newtons. That's our final answer. That's the force on charge 1. The negative sign means that overall that charge is being pushed off to the left by the combination of the electric forces between 1 and 2 and 1 and 3. So I'd like to do another example. It's a little bit more complicated because it's going to be sort of a two-dimensional example. So I want you to imagine an XY coordinate system. This is the x-axis. This is the y-axis. And we have one of our balloons. Maybe we're looking down from above. One of our balloons, balloon number 1 here, is right on the origin. And balloon number 2 is on my y-axis. And balloon number 3 is on my x-axis. And let's say that balloon number 1 has a charge of minus 2.5 times 10 to the minus 6 coulombs. And balloon number 3 has a charge of minus 1.0 times 10 to the minus 6 coulombs. And balloon number 2 has a charge of plus 4.0 times 10 to the minus 6 coulombs. Okay. And let's imagine that the distance between the center of balloon number 1 and balloon number 2 is 1 meter. And the distance between the center of balloon number 1 and balloon number 3 is 1.5 meters. Okay, so that's kind of our picture there. And what we're trying to figure out is what is the force on balloon number 1 due to the combined effects of balloons 2 and 3. Now this is going to be a vector problem because we're in 2 dimensions here. Okay? So what we're going to have to do is break this up into sort of an x problem and a y problem. So let's look at the x problem first. Okay? This means the force on balloon number 1 in the x direction only is going to be a combination of the force on balloon number 1 due to balloon number 2 in the x direction, plus the force on balloon number 1 due to balloon number 3 in the x direction. Well, if you look at the picture up here, the x direction force, or the x component of the force, between balloons 1 and 2 has got to be 0, because there is no x component. It's purely a force along in the y direction. So we can make this thing just 0. We don't have to worry about this guy. Well, the force in the x direction between balloons 1 and 3 is going to put a force in the negative direction on balloon number 1, because this will be a repulsive force, because both these balloons have the same type of charge. That's going to drive these balloons apart, which is going to push balloon number 1 in the negative x direction. So we have to make this a negative force. So I'm going to put a minus sign out here. K, Q1, Q3 over R13 squared, where R13 is just the distance between balloons 1 and 3. So working this out, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times the charge on balloon number 1, which is minus 2.5, times 10 to the minus 6 coulombs, times the charge on balloon number 3, which is minus 1.0 times 10 to the minus 6 coulombs, all divided by the distance between them squared, which is going to be 1.5 meters squared. Okay? And do this on my calculator real quick. We have 8.99 exponent 9 times minus 2.5 exponent minus 6 times minus 1 exponent minus 6 divided by 1.5 squared, and what I get when I add the minus sign in there is going to be equal to basically 0.010 newtons. Put a minus sign there. That becomes my net force in the x direction. Okay, now let's figure out the net force in the y direction. So this is going to be F1 in the y direction is going to be the force on 1 due to 2 in the y direction, plus the force on 1 due to 3 also in the y direction. Now if we look back up here, there is no y component to the force between 1 and 3. There's only a y component between the force between 1 and 2. So we can just get rid of this. It's going to be 0. Okay? So the force between these two is going to be an attractive force because this is a negative charge and this is a positive charge. And that's going to bring both these together, which has the effect of dragging balloon number 1 upwards in the positive direction. So we're going to want to make this force positive. Coulomb's constant, Q1, Q2 over R12 squared, where R12 is simply the 1 meter distance between these two balloons. So plugging the numbers in once more, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, Coulomb's constant, Q1, which is negative 2.5 times 10 to the minus 6 coulombs, times Q2, which is going to be 4 times 10 to the minus 6 coulombs, divided by the distance between them squared, which is just going to be 1 meter squared. And so plugging all my numbers in, we have 8.99 exponent 9 times minus 2.5 exponent minus 6 times 4 exponent minus 6, divide by 1 squared, whatever. And what I get is actually a negative number, but we want to make that positive. So we'll make this positive 0.090 newtons when I round it off to 2 significant digits. Okay? So now I have my two components here. I have my x component and my y component. And what I can do is I can Pythagorate these two to figure out what the magnitude... Well, first of all, I could write this vector in component form, call it F1. I could simply write it as negative 0.010 times unit vector I, actually minus, I'm sorry, plus, that's plus, 0.090 times unit vector J. I can make that all into newtons. So that would be one way of expressing our final answer, just in component form. Okay? But I could also get practice in doing this as magnitude and direction. I could sort of Pythagorate the two components. 0.010, actually technically it's negative, squared plus 0.090 squared. Make sure that my final answer is in newtons. When I do that, I get 0.091 newtons would be my magnitude. And if I want to figure out my angle from the positive x-axis, my angle theta would be 180 degrees plus the inverse tangent of the y component, which is going to be 0.090, divided by the x component, which is negative 0.010. And when I get that, I get 96 degrees. Okay, that's my angle. I had to add the 180 in here because the x component was negative, and anytime the x component of your vector is negative, then you have to add 180 degrees to the inverse tangent of the y component divided by the x component.